Hi, this is Diego Pedreros. Today I'm going to be showing you an analysis that we have done for the bell season in Ethiopia. This is a job done with Diriba, Korecha, Chris Funk, and Greg Husak. The main task that we got was to identify any changes in rainfall patterns in the bell season. To do this, we examined trends in the bell rainfalls over the last 37 years, document changes in the different characteristics such as onset of rains, duration, distribution, and rainfall totals for the season. To do this, we used the improved rainfall estimates. That is a combination of chirps and stations, even though chirps has stations, but we added more stations that we got from NMA. So that's the abstract. You can go over it. Let's take a look at the big picture. This is the annual rainfall average, and this is the variability of the annual rainfall. We see that areas in the west part of the country are less variable, that as it goes east, it gets more variable. So this is the distribution of rainfall through time and space. This is every month rainfall average. So this is showing how the rainfall moves throughout the year. So now let's focus on the bell season. This is the rainfall average for the bell. This is we can see that it is mainly on the southern part of the country, and then including parts of the northeast. It's very variable on these parts of the country, while in the southwest it's not so variable, and we see that the southeast is also highly variable. This is another way of calculating the trend. This is comparing the average of the first half of the time series with the average of the second half of the time series. So what this is telling us is that the average from 1981 to 1999 is higher than the average from 2000 to 2017. So that indicates that there is less rainfall in the second part of the time series. So now let's focus on the analysis of the start of season, the end of the season, the length of the season, and the rainfall totals. Let's take a look at how things are grown during the bell season. These are the regions for the agropastoral growing crops, and these are the regions where only pastoral areas are located. To identify the start of season of the agropastoral, we use the rules of the GOWRSI. That is 25 millimeters on a decade, followed by 2 decades that add up to 20 millimeters or more. So, and for the pastoral areas, we can identify the start of season by identifying a decade with 10 millimeters or more, plus 2 decades of 5 millimeters or more, consecutive decades. We are going to analyze these 2 polygons specifically, and I'm going to show you the process that we're using to identify all the different variables. So this is a complete year of rainfall. This is the decade 1 to decade 17. That's where we are going to identify the bell season. The bell season, based in talking to Diriba, we identified from decade 4, that's the first decade of February, to decade 17, that's the second decade of June. So once we identify that, those decades, we started looking at what would be the first decade that fulfilled our first rule, that's 10 millimeters or more. So that would be this decade, that's decade 10. Then followed by at least 5 millimeters in the next 2 decades, then this will be the start of season. To identify the end of the season, then go to decade 17 and go backwards. And the first decade that was 5 millimeters or more, then that would be the end of the season. So once the rainfall drops before decade or up to decade 17, then that would be the end of the season. So these two complete our season. So then the difference between these two decades will be the length of the season. Then to identify the sum of the season, since the length of the season based on the start and end of the season was very variable, sometimes it was very small, sometimes it was a long season, and besides that there were periods of time where there was some rainfall before we identified the start of the season. So there were some small amount of rainfall in decades, but not enough to complete the rule. Then we decided to go for all the years from decade 4, so that's the first decade of February, to decade 17. So that way we'll be able to compare and include all the rainfall. So that will be the total rainfall in millimeters that we're going to compare. Then let's take a look at all these different variables in the polygon that is right here, this one, 47707. Then the red line is telling us the length of the season from the start of the season decade to the end of the end decade. So this is telling us, based on this axis right here on the right, is telling us how long the season was. We see that it's very variable. We don't see a well-defined trend, and we see that sometimes the season could last more than 10 decades, or sometimes only 3. The blue bars are showing the seasonal total, and this seasonal total is the sum of rainfall from decade 4 to decade 17 for the same for all the years. So we see that there is a little bit of trend for that for the rainfall totals, even though the length of the season doesn't have a trend. Then to see how much rainfall was lost or gained during the time series, so I calculated the percent of median. So the way I did it was calculate the median for all the seasonal totals, regress that against time, took the slope, multiplied the slope by 37 years, and took the percent of the median. So in this case, we are losing 33% of the median in that polygon during the time series. So that is for polygon 47707. And here we show the profile, the rainfall profile for that polygon. It begins at the end of February. Usually the rainfall begins at the end of February, has a peak at the end of May, at the end of April, beginning of May, and then it goes down. So that is this polygon. Now let's take a look at the next polygon. This polygon is the one in here. That is a pastoral area. So let's see how that polygon is behaving. So again, this is the length of the season. We see a clear trend, even though it is very variable, but it's showing that the length of the season is decreasing. Then we look at the total rainfall. Then it's showing also that it's decreasing. And the profile is showing us, again, rainfall begins probably in February, sometime in February, it peaks around April, and then it goes down to June. So to find out how much rainfall has been lost in this polygon, we calculate the median, took the slope of the regression, multiplied by 37, and then took the percent of the median lost. In conclusion, the bell season have been declining, especially in the last decades. It is clear that the agricultural areas during the bell season are shrinking due to shorter rainfall season, as well as a decline in the amount of rainfall. This is creating more dependency on the current season for agriculture. Also, historically, the northern and central Rift Valley regions of Ethiopia are prone to severe drought. And with this process, we have shown similar findings. And so we could apply this process to other places. And finally, we need to tune better the end of the season amount for the decades, and so that to get better results. So that's it for today. Thanks.